So problem number one said the user properties of limits to determine the following. The limit as x approaches 4 of x squared plus 3x over x squared minus x minus 12. Okay, well, as x approaches 4, the numerator approaches 28 and the denominator approaches 0. And well, if you look at it, this really is just a translation of 1 over x. And so the two-sided limits are actually not going to equal. They're going to be equal, so the limit will not exist. But so I don't really need to simplify this to show it, but it makes my life so much easier. So let me simplify. Factor out an x factor. And so you can simplify this. The limit as x approaches 4 of x over x minus 4. So let's look at each of the one-sided limits to show that the two-sided limit does not exist. Let's take values of x greater than 4. Let's insert one more page here. Okay. Okay, so, well, as x approaches 4, the numerator is positive. The denominator goes to 0, but it's positive. So positive over positive is positive. Something bounded divided by something going to 0 goes to infinity. And so this goes to positive infinity. Let's look at the limit as x approaches 4 for x is less than 4. And so the numerator, well, it approaches 4, so that's positive. The denominator approaches 0, but if x is less than 4, then x minus 4 is negative. And so positive divided by negative is negative. And so in this case, it goes to negative infinity, since it's a bounded number over something going to 0. Well, these are not equal. Limit as x approaches 4 is not equal to limit as x approaches 4. So the right and left sided limits are not equal. Therefore, my limit does not exist. And so the original, and maybe I should write the original, whatchamacallit. Oops. Let me write the original limit here. So the limit here as x approaches 4 of x squared plus 3x over x squared minus x minus 12, therefore does not exist. So your answer is, well, this limit does not exist. let me do problem number 2. Determine the following limit. The limit as x approaches 0 of the sine of x, where the sine of x is negative 1 if x is less than 0, 0 if x is 0, and 1 if x is greater than 1. This is a standard function that people use. Oops. So I'm going to do it the same way we did the previous problem. So in this case, I'm going to consider the one-sided limits. So let's look at the limit. As x approaches 0 from the right side of the sine of x. Well, if x is greater than 0, sine of x is always equal to 1. And so this is just equal to 1. Maybe I should just put it here. So the sine of x, as we're approaching 0 from the right-hand side, will always equal a positive 1. Let's look at the limit as x approaches 0 of the sine of x. So we're approaching here from the left. Well, if x is less than 0, then the sine is always equal to negative 1. Limit of negative 1 is just negative 1. Now the left and right side limits are not equal. Oops. This is not equal to the limit as x approaches 0 from the right side. Oops. Right side limit. And so this limit does not exist. Okay. Let's do problem number 3. Determine the following limit. The limit as x approaches pi over 2 of the floor of cosine of x. Well, cosine of x and maybe I should say this. So cosine of x is between, let's see, 0 and 1 if x is in the first quadrant. And so if x is in the first quadrant, cosine is between 0 and 1. It's 1 at 0, and it's 0 at pi over 2. So cosine of x is positive in the first quadrant. Therefore, and it's less than 1. Therefore, its floor is 0. The greatest integer less than something between 0 and 1 is, well, 0. Oh, maybe let's do one more line down. So this is for x. Of course, actually, it's true if x is equal to pi over 2, but we're doing a limit, so we don't care about pi over 2. So therefore, the limit, again, I'm going to be looking at the two-sided limits here. The two one-sided limits. I misspoke. So let's look at the limit as x approaches pi over 2 of cosine of x. And we're doing the floor of this. So this is equal to limit as x approaches pi over 2 of 0. It's a very nice function. And so in this case, for x is near pi over 2, but greater than pi over 2, it's going to equal, well, 0, always. And so the limit of 0 is just 0. So this is 0. Let's look at the cosine of x between pi over 2 and pi. So if x is in the second quadrant, well, if x is in the second quadrant, then cosine of x is going to be, well, between -1 and positive, between -1 and 0. So it's always going to be negative. It's going to be between -1 and 0. So therefore, the floor of cosine of x well, what's the greatest integer? Less than or equal to some number that's between -1 and 0. Well, it's going to be -1. And so, and this is for all of these. And so for x in that interval, for x between pi over 2 and pi. Therefore, the limit as x approaches pi over 2 of the cosine of x, and maybe I'll just write it here, is the limit as x approaches pi over 2. As you're approaching from the left, well, it's always equal to -1. Near, of course, I'm talking about near. So for x is near pi over 2, but less than pi over 2, my function is always equal to -1. And so its limit is just -1. Well, these limits aren't equal. So I guess the tendency here, I guess all of them work equal. So the limit as x approaches pi over 2 of the floor of cosine x is not equal to limit. 1 is not equal to -1. The limit as x approaches pi over 2 from the right, I'm sorry, from the left of the floor of cosine x. Therefore, the two-sided limit of the floor of cosine x does not exist. Okay, so you're done. Give a counterexample to the intermediate zero theorem where only rational numbers are defined. So the intermediate zero theorem was a theorem that said that if you had a continuous function on the real numbers, and so if you had a continuous function on a closed interval that's real, then if at one endpoint, if the signs of the function are different on the endpoints, then somewhere in between, then somewhere in that interval, that real interval, closed interval, we must have that the function is equal to 0. So let f of x, oh, I guess let, oh, I don't know, let's say 0 to 1. So let me use this notation. Let 0 to 1 sub q be the closed interval that only consists of rational numbers between 0 and 1. So it's the set of all rational numbers between 0 and 1. Then let me define f, and let's say it goes from 0, 1 to, I don't care, let's say -1, 3, I think. Let me move this over so I have more space to write that. Okay. Okay. Let me get out of this corner so I can write it. Okay, so the f of x equal (2x squared minus 1). So at 0, it's -1, and at 1 is 3. Okay, good, good. That's what I was thinking in my head, so I just wanted to check. So this is a continuous function. So then f is continuous. All the same, everything involving limits and all that, and continuity of polynomials all works if I'm dealing with rational numbers. That's not going to change. The definitions are all the same, other than restricting everything to be only involving rational numbers. So nothing changes there. So I have a continuous function on a closed interval. So the intermediate zero theorem holds. However, this function is never zero. And so however, f of x is not equal to 0 for all x in this closed interval. It's 0 at 1 over radical 2, but of course 1 over radical 2 is not a rational number. And so that's a contradiction. So I have defined I have given a counterexample to the intermediate zero theorem. And so this function satisfies the intermediate zero theorem, except that, of course, I'm only dealing with rational numbers. So the intermediate zero theorem only works for real numbers. If I restrict it, if I've only defined my rational numbers, this intermediate zero theorem just does not hold. Okay, so. Let me determine the values for which this function is, well, continuous. Oops. Let me. Actually, if I note here, this function here, it looks a little better, is actually the same as saying that f of x is equal to the floor of x if x is rational and is equal to minus the floor of negative x if x is irrational. Okay, so so the thing is that, well, if you have, so this is not going to be continuous anywhere. So this function will not be continuous anywhere. Is not continuous. Anywhere. Okay, so let's just suppose okay, come on. So first, let's look Well, maybe I'll give you the idea. So suppose I had some number here, and it was between n and n plus 1, okay? And it's positive, okay? Then, if I take a rational number in here, then the floor will equal n. So it'll equal n for x being rational. But if I take an irrational number, then the irrational number will be between negative n minus 1 and negative n. And so it will equal negative n minus 1 if x is irrational. And so if you take some, maybe let me take actually, let me give you an actual like number. So let's say I have 1.5. Take some number 1.5, okay? Then the floor of that is 1, okay? So you just get this number here, 1, okay? Now, take a number, irrational, but near, say 1.5. So just take some irrational number near 1.5. And so if you take some number near, it's irrational. So let's say take some irrational number. I don't know. Let's take 1.510100100, etc. Okay, so that's some irrational number. So then you're going to get, well, let's look at minus that. Okay. So its floor would be negative 2. So if you try to approach any number between 1 and 2, okay, so take any number, I don't care, rational, irrational. Well, there's always, in between any two rational numbers, there's an irrational number. In between any two irrational numbers, there's a rational number. So as you take values between 1 and 2, this keeps oscillating between, well, for rational numbers, I get a number of 1. For irrational numbers, I get negative 2. So it keeps oscillating back and forth between 1 and negative 2, depending on if I'm choosing a rational number or irrational number. And well, it'll do the same thing for any sort of k, or n, I guess. So f, so let's suppose that, so let x be some number between n and n plus 1, for n being some whole number. Actually, it doesn't have to be a whole number. Well, yes, it will, if I want to write a formula down for it. Okay, so let n be a rational number. And so, because I'll have to check if the formula changes. So then, this will equal n if x is rational. Okay, and it'll equal minus n minus 1 if x is irrational. So therefore, the limit as x approaches, let's say, a, of f of x will not exist if a is greater than or equal to 0. Now we'll have a similar formula for x less than 0. So if a is greater than or equal to 0, well, it keeps us, in other words, oh, and I guess I should say this, since between, and this is actually, this is an important fact that I'm using to show that the limit doesn't exist. So the fact that no matter what, you're going to get values that are both, as you approach any value a, you're going to get a value that's either equal to n or minus n plus minus 1. Because, well, between any two rational numbers, there is an irrational number. And so if you're trying to approach some rational number, it's going to oscillate back and forth. And also, between any two irrational numbers, there is a rational number. So it keeps oscillating between n and minus n minus 1. Now, we have the same thing if n were negative. And so it's just, so let x be between negative n minus 1 and negative n. For n being, well, yeah, some whole number. Okay, then f of x is equal to minus n plus 1, minus n minus 1, sorry. If x is rational. And it's equal to n if x is irrational. Yeah, so unfortunately, I can't combine. I almost am able to combine these, but I can't. Oops. That was a typo. Where was the irrational? Oh, that was a typo there. That's it. Should have said irrational. So I can't quite combine these two into one formula, but almost. Okay, so again, this limit doesn't exist. So the same reasoning as above. I'm just going to copy it, and I'll just say it. So copy. It's the exact same reason. There's no. So this limit doesn't exist if x is, well, less than 0. And so since between any two rational numbers, there's irrational numbers, and also between any two irrational numbers, there's a rational number. Therefore, the limit as x approaches a of f of x is equal, it does not exist. Therefore, well, since it didn't exist, if a were positive or if a were negative, well, it doesn't exist anywhere. And it also doesn't exist for 0. So I've shown that it doesn't exist anywhere. So f is, or whatever, the limit doesn't exist anywhere. Since the limit doesn't exist anywhere, it's not continuous. So this the limit here never exists, doesn't exist for any number. And so because of that, I have that my function is not continuous anywhere. Okay. Oops. Any questions about those? Okay. So let me do problem number 6. Determine the location of any removable discontinuity for the following function. Well, first off, we have, so f of x equals x squared minus 1 over x plus 1. So first off, this is a rational function. And I know that a rational function is continuous everywhere in its domain. So the only possible discontinuity is where it's not in the domain. And so the domain of f is a set of all x's not equal to -1. Therefore, f is continuous for x. For all x's except, oops, for x equaling, possibly, for x equaling -1. Well, if you plug in -1, well, you're dividing by 0. So it's, the function doesn't exist there. And so it's certainly not continuous there. So let's check if the limit exists. If the limit exists, then we have a removable discontinuity. So I should probably say that f is discontinuous is not continuous. When x is equal to -1, because it doesn't exist when x is -1. And the limit as x approaches -1 of f of x. Well, is equal to limit as x approaches -1 of x squared minus 1 over x plus 1. So this is limit as x approaches -1 of x minus 1, x plus 1 over x plus 1. Well, I can cancel the x plus 1s, and I just get x minus 1. And so this function is equal to x minus 1, except when x is equal to -1, but I'm doing a limit as x approaches -1. And so since they're equal everywhere except for -1, well, then the limits are equal. And so as x approaches -1, x minus 1 approaches -2. Since the limit exists, and since the function is discontinuous at that particular point, then I have a removable discontinuity when x is equal to -1. So f has a removable discontinuity at x equal -1. Okay, so you found the location of your removable discontinuity. Let me do problem number 7. Determine the limit of the following difference quotient. The limit as h approaches 0, f of a plus h minus f of a all over h, where f of x is equal to 1 over x plus. That's a weird way of saying it. I meant to say f of x is equal to 1 over 1 over x plus 1, and a is equal to 1. And so let's determine my difference quotient. Oops. The limit of this difference quotient. So the limit as h approaches 0 of f of a plus h minus f of a over h is a limit. Oh, I need to go 1 down. Limit as h approaches 0 of 1 over, I'm going to replace x by a plus h, which in this case is 1 plus h. Minus, replace a by 1. So let's determine f at 1. So we replace x here by 1. 1 over 1 plus 1. All divided by h. Okay, so limit h approaches 0. Oh, actually, let me do 1 more down. Of 1 over h plus 2 minus 1 over 2 all divided by h. So the first thing I want to do here is get a common denominator. The common denominator is 2 over h plus 2. And so this is the limit as h approaches 0 of 2 over 2h plus 2 minus h plus 2, so minus h minus 2, all divided by h. So there's a limit as h approaches 0. The 2's cancel. So you get minus h over h plus 2 times, well, I'm dividing by h is the same as multiplying by its reciprocal. 1 over h. 1 over h is cancel. So this is equal to the limit as h goes to 0 of a negative 1 over h plus 2. Well, as h goes to 0, this approaches negative 1/2. And so that's your limit, negative 1/2. Let me do problem number 8. And so prove the following theorem using epsilon delta. You may not use any limit theorem in the proof. So just epsilons and deltas. Limit as x approaches a, f of x equaling L, and limit as x approaches a of f of x equaling m implies that L is equal to m. So basically what you're trying to do is show that limits are unique. So a limit, if it exists, will be unique. So let's show this. Since the limit as x approaches a of f of x is equal to L, then, well, let me write the epsilon delta definition. Then, for any epsilon greater than 0, there is a delta greater than 0 such that if the absolute value of x minus a is between 0 and delta, then and I think I'm only going to do this for the first one, then f of x minus L is less than epsilon. Therefore, since let's do 1/2. 1/2 L minus M is greater than 0, then. So now what I'm going to do is I'm going to say, well, 1/2 L minus M in absolute value is greater than 0. So I can let that be. I'm assuming here L is not equal to M. If L were equal to M, then I'm done. So let's suppose L is not equal to M. So suppose L is not equal to M. Since one half absolute value exists, a delta 1 greater than 0, such that x minus a in absolute value being less than delta 1 implies that f of x minus m minus L is less than 1/2 L minus M. Okay. Also, well, I can do the same thing for this one. So since the limit as x approaches a of f of x equals m, I'm not going to write it out. You know, it's the same here. Then and since 1/2 L minus M is greater than 0, so we can make that a nice, like, oh, come on. I can make that my epsilon. Then there exists a delta 2 greater than 0, such that delta 2 greater than 0, such that if x is between, if x minus a in absolute value is between 0 and delta 2, then f of x minus m in absolute value is less than 1/2 L minus m. And so, therefore, we have the following. L minus m I need one more. Is equal to, well, f of x minus m minus f of x minus L. the f of x cancels, then you have a minus m minus a minus L. So that's L minus M. Okay, so by the triangle inequality, this is less than or equal to f of x. Oh, you stupid. Therefore, let delta equal the minimum of delta 1 and delta 2. So forgot one line here. Then x minus a in absolute value being between 0 and delta. Then I have that L minus M is equal in absolute value is equal to the absolute value of f of x minus M minus f of x minus L. By the triangle inequality, this is less than or equal to f of x minus M plus the absolute value f of x minus L. But since x minus a in absolute value is between 0 and delta, then x minus a in absolute value is between 0 and delta 2. And so therefore, we have that this first absolute value is less than 1/2 absolute value of L minus M. Next, since x minus a in absolute value is between 0 and delta, then and delta is the minimum of delta 1 and delta 2, then x minus a in absolute value is between 0 and delta 1. And so we have that the absolute value of x minus a of the absolute value of f of x minus L is less than 1/2 L minus M. So this is also less than 1/2 L minus M, which is L minus M. But how can the absolute value of L minus M be less than absolute value of L minus M? How can 12 be less than 12? You can't have that a number is less than itself. So that's a contradiction. So that contradicted the fact that my supposition that L was not equal to M. Therefore, L must equal M. Otherwise, we get a contradiction. And so I've shown that L is equal to M. And that's, so I'm done. Okay, so that proves that. Any questions on that? Okay. Problem number 9. A rectangle has perimeter of 20 meters. And so the perimeter is 20 meters. And express the area, well, the area maybe I'll just, okay, so the perimeter is 2L plus 2W of a rectangle, and the area is L times W. We're given that the perimeter is 20. And I don't know, let's say that one of the sides is X and the other one is Y. So let's call it X and Y. Okay. So that says that 2X plus 2Y is 20. Therefore, X plus Y is 10, dividing every term by 2, subtracting X from both sides of my equation. You get that Y is equal to 10 minus X. And so the area of a rectangle is length times width. And well, I solve for Y. Therefore, the area is 10x minus x squared. So that is the area of my rectangle as a function of one of the lengths of its sides. Let me do problem number 10. Prove the following theorem using epsilon and delta. You may not use any limit theorems in the proof. The limit as the limit as h approaches 0 of f of a plus h equaling L, if and only if the limit as x approaches a of f of x is equal of f of x minus L is equal to 0. Okay, so let's try to prove this. And let's do this way first. So let's suppose that the limit as h approaches 0 of f of a plus h is equal to L. Then, given epsilon greater than 0, there exists a delta greater than 0 such that if h were less than delta, then f of a plus h minus L is less than epsilon. Okay. And this is true for any h satisfying that. As a matter of fact, it's true if h were equal to x minus a. So then, oh, come on, I'm just trying to scroll. So, in particular, when h is x minus a. So let's just state that. So given epsilon greater than 0, there exists a delta greater than 0 such that if the absolute value of x minus a is between 0 and h, then and let's leave some space here. Well, let's leave some more space than I need, and then I'll scroll. Okay, so then absolute value of f of a plus h minus L is less than epsilon. Okay, so this is the same as f of x minus L. So I really haven't, I've just sort of, the a's cancel. But this is the same as f of x minus L minus 0. Okay, so now, oops, I don't need an equal there. So now I can read what this says. But this says that the limit as x approaches a of f of x minus L is 0. And that's what I wanted to show. And so I'm done with that. So I've shown this direction. So now I want to show the other direction. So let me show the other direction. It's just as easy. And so let's try to prove that. Again, by the definition of epsilons and deltas, we have the following. So since the limit, so here I'm assuming that this limit here is equal to 0. So since this is equal to 0, then given epsilon greater than 0, there is a delta, there exists a delta greater than 0 such that if x minus a in absolute value is less than delta, then f of x minus L minus 0 is less than epsilon. Okay, good. And so, again, we're going to do this sort of using the same trick we did before. I'm going to let h equal x minus a. And so let's do that. So in particular, for h equaling x minus a. In other words, when x is equal to h plus a. Okay. And so this says that given epsilon greater than 0, there exists a delta greater than 0 such that, well, zero is less than or equal to h is less than delta implies that 0 is less than, well, h plus a minus a. That's just a particular, certainly the a's cancel. And so the a's cancel. And so that's just h. But in particular, this is, well, one of these. And so this is going to be, well, let's see, I want to show this. Get rid of that. So I want to show this here. So let's look at, what does this say about f of x, f of a, sorry, f of a plus h. Oh, I should have called this a plus h. Not that it really matters. Just so that it goes with what I wrote. And so f of a plus h minus L. Let's see what this is equal to. Okay. If I can show that this is less than epsilon, then I'm done. Okay, so this is equal to f of, well, a plus h minus L minus 0. Okay. And so I have here that if I have any x in particular, a plus h, I mean, it could be 43, it could be 12, it could be a billion, it can be a plus h. And so if I have that the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus L minus 0 is less than epsilon. And so since x minus a in absolute value is between 0 and delta, then this is less than epsilon. But that means that this guy is less than epsilon. And so, in particular, it says that the limit as h approaches 0 of f of a plus h is L. And that's what you wanted to show. And so I'm done. Since I've shown each of them, then I'm done with the if and only if. And so that finishes off